accurate, and we're lucky that Bellingham is close enough to the border that they have charts for Bellingham as well using these Canadian weather maps, and they are incredibly accurate. As you know, living in this coastal climate can be very unpredictable, and those maps are really good. So I thank you that we get to share in them as well. So yes, my name is Kristen Larson, and I'm a faculty member at Western Washington University in our joint Department of Physics and Astronomy. And what I'm going to show you tonight is some of the things that I find most interesting about dust. And I'll tell you a little bit more about what that is. And I encourage you to stop and ask questions if they come to you at any point. But without further ado, we will begin. So, and I have to learn how to use my little thing here. Tonight I'm going to talk about the interstellar medium. That's the polysyllabic version. And interstellar just means between the stars, and medium means stuff. So it's the stuff between the stars. And it's really made out of gas and dust. You'll learn very quickly that I am incredibly partial to one of those two. So we'll get the one I'm not that interested in out of the way, and we'll talk about the gas. So what the gas does in our galaxy, in our universe, besides hang out, is it glows. And if you've ever seen a neon sign, that says "Eat it, Joe's," it's this red color, and the reason why it's red is that's the signature color of the neon atom. So if you pump a bunch of energy into the neon atom and then it cascades back down to its ground energy state, it happens to emit a lot of this red light. If you've ever seen a sign, though, that is not red, we call them neon signs, but they're not really neon signs. They're made out of some other gas. And in fact, the various gases in the universe glow at these different colors because of the combination of spectral lines, and it just depends on the type of atom. So the set of colors you get is the fingerprint of the atom. So these are argon and xenon and helium over on the left-hand side. By the way, I should mention helium. My favorite story about the gas helium is it was discovered, those spectral lines, that sort of funny orangey color, the set of spectral lines was first discovered in the spectrum of the sun, and they didn't know what it was. So they named it after the sun god, Helios. That's why we call it helium. So you may know that helium's actually tricky. It's not like you just whip it up in your kitchen. It comes from like mines and places anyway. So it was hard to isolate. So it was actually first seen in the spectrum of the sun. So here's some more of these lines. And there's one in particular that I want you to see, because it's the one that we see the most in the universe. And it's this one. This is hydrogen. This is, and that distinctive pink color comes from, if you spread it out into its constituent wavelengths, it turns out that it's a red line and this like tealy line and then kind of a bluey purpley line. And when you combine them all together, they make this pink glow. And if you have taken color pictures with your telescope, you have seen this particular pink. And it's because most of the universe is made out of hydrogen, including the gas of the interstellar medium. So it's this pink I'm talking about, this pink right here. So anytime you see these pictures of these nebulae, it just means things that are fuzzy. That's a huge range, especially through the turbulence of the atmosphere and poor seeing. It's kind of fuzzy. But anyway, that's not what I'm talking about. I'm talking about objects that are intrinsically not point sources. They're not stars. And you've seen many pictures like this. You may know that this is the Horsehead Nebula. I have no idea how it gets that name. No, that's a joke. Actually, it kind of looks like a horse. Yeah, so stay with me here, people. Okay, but the pink is that same glow. It's the exact same glow from a tube of hydrogen. And there's hot stars nearby that are pumping energy into that hydrogen gas and making it glow that pink. But of course, gas is not what I wanted to tell you about. I wanted to tell you about the other part of the interstellar medium, and I wanted to tell you about dust. In particular, space dust. No, not house dust. That's mostly dead skin cells, I've heard, which is disgusting. We're not going to talk about that. Instead, space dust it's actually maybe not terribly well named. It's really more soot. So soot is dark carbonaceous kind of stuff left over from burning. The soot is similar to some of the kinds of dust that we have, and the other kinds of dust that we see are things that are made out of silicates, basically sand. So small particles finally, they weren't ground from bigger things, they started out small. And we'll talk about where this stuff comes from and a little bit more about what it is. But the most important thing for astronomers, whether we are appreciating the beauty of the universe or trying to understand the history of the universe or whatever it be, is that the dust profoundly affects our view of the universe. And so it was actually discovered, this one particular piece of what dust does was discovered by this astronomer named Trumpler. And it was discovered in 1930. It actually amazes me that it took so long to discover this particular feature of what interstellar dust does. But I'll explain to you how he figured it out. So he was looking at these clusters of stars. And when he saw these clusters of stars that were faint, maybe like this one is a little bit faint, and he assumed that meant that they were very far away. That's one of the ways things get faint. And as far as people knew, it was the only way that things got faint. And he then started to actually look at the size of these clusters, and he found that the star clusters far from the Earth are much, much larger than the star clusters near the Earth, which makes no sense whatsoever. And so he realized that those clusters aren't far away and big, they're actually close and smaller. I tell my student this is it's a bird, it's a plane, it's Superman phenomenon. Like, how could you possibly get confused? Well, a bird is small but nearby. Plane is large but far away. And so he realized that something else must be making these things dim. And if you take that thing away, they're actually much, much brighter. It turns out that there's something in the way that's making them dimmer, not dinner. I just had to dimmer. And so what he discovered was that dust dims the starlight. So you may have been wondering about the horse here. And the horse is actually that there's dust in the way, and it's blocking the background starlight. So that's what makes it seem very, very dark there, is that there's this thick, thick dust in the way. And in fact, if you look all throughout the sky, you can see this phenomenon. So this is an AllSky Mosaic from photographs, actually. This is by he was a faculty member, I think, at one of the state schools in Michigan. But he has two versions now, one done with photographs and one done digitally. But he does these all-sky images. So the sky is a big place, actually, and it's not an easy thing for those of you who have done the hard work of stitching together images to stitch them together over the whole sky. And he's rearranged this picture so that the Milky Way runs right through the middle. And so the Milky Way is actually the plane of the circular disc-shaped galaxy that we're located in. And if you look at this for a while, the stars are awesome. You see those right away. But then one of the things you're going to see is those dark lanes that run through the Milky Way. In fact, there's dark patches all over this picture. This is a picture from Ontario, but I picked it because it was sort of more or less in the same kind of latitude range where we are. We don't, up north where we are here in Bellingham and the Sunshine Coast, we don't get the huge view of the bulge of the Milky Way. But we do see it on the horizon. And these dark lanes here, in fact, every culture of the world that lived in a place that could see these dark lanes through the Milky Way have stories about them. Whether it was, and the Australians called it a neck of an emu, which is a giant flightless bird. Other cultures called it a river, a dark river. And so what you're seeing here is not a lack of stars, but simply that dust blocking the background starlight. So here's one of my favorite pictures of that. My college students always get really excited when they see this because they want it to be a black hole. I'm sorry, it's not a black hole. It is, however, a very thick cloud of dust. And if this dust were between us and our sun, we wouldn't be able to see our sun at all. So these are called Bach globules. And this is Bernard 68, one of my favorites. And you can tell right away here, right, that there is a lot of dust here blocking that starlight. But there's something else that's going on here, and to really see what's going on, you have to sort of look at what's going on in the edges of the cloud. And so if you sort of zoom in there, you'll see that a lot of these stars are red in the edge of the cloud. Now, if you look in the upper left-hand corner, you'll see that there's just lots of, blue stars and white stars and yellow stars. In fact, the stars that appear red here are probably just as blue as the stars in the upper left-hand corner. It's not just that they're dim, and they aren't quite dim, as you can see, but they're also very red, and those two things are both actually caused by the dust. So not only does dust make things dimmer, it also makes things redder, especially the background stars. So how does that work? Well, how that works is that the dust is very effective at blocking out short wavelength light, like blue light. So if you look at a picture of Bernard 68 in blue light, it looks like this. And you can see that it's doing a terrific job at blocking out all of that blue light. If you take off the blue filter from your telescope and you put, say, a green filter on, astronomers sometimes call this the V band, you can notice that some things are starting to actually kind of poke through. The dust is not doing such a good job at that. And if you move into the red, well, now more and more things are coming through. And as you go to longer and longer wavelengths, say into the infrared, now you can, see tons of background stars and even longer wavelengths and even longer wavelengths until you pretty much can't even tell that the cloud is there. Mm-hmm. So if I make a composite of both the optical wavelengths and the infrared wavelengths that our eyes are not sensitive to, but cameras can be made sensitive to, and film, once upon a time, sensitive to the infrared, then you get something that looks like this. You get these two things together. So how it makes things look redder is it takes out the short wavelength light, the blue light, and leaves the long wavelength light, the red light, to shine on through. And I have a demonstration actually of this. And my poor husband knows that I've become obsessed with this stuff called opalescent glass. In fact, we stopped in your bead shop today in town, and the lady was very nice and was chatting with me, and I was totally uninterested in the conversation because I was hunting through the entire store looking to see if she had any opalescent glass. Fortunately, she did not. Fortunately, I brought some of my own. So I'm going to pass this around, and here's what I want you to notice about it. I want you to notice that when you hold it up to the lights in the ceiling, and you look through it, okay, it looks kind of reddish when you look through it. But if you just hold it in your hand, it actually looks blue. And I'm going to start with our youngest audience member here, and he will take a look at that, and then he will pass it along. And then I have a bigger piece here of this opalescent glass. There's nothing fancy about this, but and I want you to, first of all, here's the mag light, right? It's just regular color. Can you see how red that looks? It's just a piece of white glass that I got at the gift shop at SeaTac. You find this stuff everywhere. I don't know why. But anyway, so see how red it looks when it's coming through all of that opalescent glass. The red light is coming through. The light started out to be kind of regular yellowy, but it's looking pretty orange by the time it makes it through. Where did all that short wavelength light go? I mean, where did all that blue wavelength light go? See the bottom of the egg? See how all that blue light is scattering around? In fact, that blue light has scattered more efficiently than the red light. And so the fact that the star looks red can go along with the idea that the surrounding material can look blue. So if these colors are starting to sound familiar to you, this is in fact the same reason why sunsets are red and our own sky is blue. These processes are most efficient at short wavelengths, and when the sun's on the horizon and you're looking through, not that you would do this because you're all astronomers, you're all outside getting ready for the darkness, but the sunset looks red because it's coming through a lot of the atmosphere. So we see both of these effects, the reddening and the dimming, and a third effect, this blue reflection when we look out into the universe. So I'm just going to show you a couple of pictures here of clumps of gas and dust in the interstellar medium, and I want you to look for these things that we've talked about. So the dark part is from the dust blocking the starlight. Where you see all these yellow stars, you're thinking, what a coincidence, all those yellow stars. Probably not, It's probably that there's a thin layer of dust there at the edges of the cloud, making things look oranger and yellower and redder than they would have been if the dust were not there. And then all that blue stuff out there is the light reflecting, sometimes astronomers call it scattering, off of the dust grains. Now, the pictures I'm going to show you here are all from one of my favorite sites to find ground-based astronomy images. These are from the Canada, France, Hawaii telescope. And if you go to Hawaiian Starlight, if you Google that, or maybe it's hawaiianstarlight.com, they have really, really fabulous pictures, and they're true color pictures. That's the thing I like about them. They don't take these black and whites and then like color them weird, funky colors. These are true colors here. So this is the Horseshoe Nebula. Again, you can see the dark. Where does the pink come from? This quiz. Gas, hydrogen gas. And the blue is the reflection off of the dust. And this one's probably my favorite. This is the Cocoon Nebula. Excuse me. And I'll tell you by the end of this talk why this particular nebula is very well named the Cocoon Nebula. But for now, I want to take you to one that we've observed quite a bit. This is the Trifid Nebula, and this is M20, Messier 20. Messier made a catalog of fuzzy things because he was hunting for comets, and the other fuzzy things that weren't comets kept annoying him and distracting him. And so he made this catalog that is well known to amateur astronomers as sort of the great deep sky object catalog. Anyway, this was number 20 on his list of annoyances. You know, all this color I've been showing you, if you've only put your eye up to telescopes, you might think I'm making this up because, you're thinking, really, I have not seen these colors. The problem is that in low light conditions, our eyes are not very sensitive to color. If you walk around your house at night, you should notice that all your upholstery looks kind of muted, right? Cameras don't have this problem, actually. They don't even have to be fancy ones. Film and camera, you just leave the shutter open long enough, and it will detect these colors. So these colors are real. This is what you might see with your eye. This was taken at the Kitt Peak Male 4 meter. I guess they probably don't have eyepieces on the Kitt Peak 4 meter, but if they did, this is what it would look like. But here's what it looks like in color. And so you can see all this pink from the hydrogen gas and the blue from the dust and those beautiful dark dust lanes. Okay, so let's say you wanted to take a closer view. Okay, if you wanted to take a closer view, and those of you who know a little bit about the history of the Hubble Space Telescope recognize this distinctive chevron shape. And in fact, the early pictures from the Hubble's telescope had this shape, and Hubble did go and zoom in and look in here, and this is one of the more famous pictures from the beginning sort of decade of the Hubble Space Telescope. So this object is 9,000 light years away. The image is 7 light years across. These are called evaporating gaseous globules. Wait for it. Eggs, EGG, evaporating gaseous globules. There's no one better at TLA's 3-letter acronyms than astronomers. No one. Okay. These are the evaporating gaseous globules, or eggs, and there's a reason for that. It's because what's happening here is that stars are forming. The gas and dust has become so dense that eventually the hydrogen in the core of this globule will fuse into helium, and that's what we call a star. So you're seeing a little baby newborn star there, and it's emerging from the material from which it formed because there's a hot, hot star off upper stage left that's blasting away the rest of the interstellar medium. Even that stalk that it's on is 3/4 of a light year long, that little stalk. And so buried deep in there is a star. So how do you look into that? Because now we really want to know, right? And how you do it is you use infrared light, because the infrared light, right, longer wavelengths, sails right through the dust. And so remember, this is the picture of what the whole sky looks like, and there's all that dark part, because of all that dust. If you look in the infrared, the near infrared, this is what it looks like. See, now you can, well, not totally, because there's still a lot of dust, but now more. You can see quite a bit through here. I should mention to you that one of the things that's amazing to me about this picture is that when I did my PhD thesis back when dinosaurs roamed the earth, I went to a telescope to measure near-infrared star brightnesses. And for each star, I would measure 3 colors, and it took me my whole PhD career to apply for the time and go on telescope, and I measured 107 stars. The whole thing fit, all the numbers fit on one, letter-sized piece of paper. This survey, the 2-micron AllSky survey, did exactly the same thing for 750 million stars. So where a lot of astronomy research comes from now are these all-sky surveys, not just like a couple things, but these all-sky surveys with hundreds of millions of objects. So back to the story low at hand. So here's the Trifid Nebula again in the visible. Here's what it looks like in the infrared. Now there's actually two different pictures superimposed. On the right here is IRAC. The top picture shows sort of the filaments from the warm dust, and MIPS is the even longer wavelength stuff, and they're combined into this middle picture. I'm sorry they chose green for infrared. Hey, they didn't ask me, okay? But you can see how different it looks, right? And plus you can see that there's these little globules that you just don't see in the other image. And infrared astronomy started in really the late 80s. It's not that old. People haven't been able to do this for very long, and we didn't know very much about how stars formed before infrared astronomy. And when you zoom way in, right, then you see things that look like this. So the arrows in the right-hand side are pointing to these little objects, and the arrows on the left-hand side are pointing to, well, nothing, because you can't see them. You can't see them in the optical. So, the Hubble Space Telescope is probably, the most amazing space telescope that we've ever launched. But what made it so powerful is these other telescopes that complemented it. And so this is from the Spitzer Space Telescope, maybe not as famous as Hubble, but still did amazing, amazing observations in the infrared of how these little guys form. Okay. So it's impossible for me to talk about the interstellar medium in February without mentioning the best case of observing the interstellar medium, and that's the Orion Nebula. As I mentioned to some folks at dinner, we take telescopes out at Western underneath these security lights. So I'm quite limited into what I can actually see. And even I can find the Orion Nebula. Orion is very distinctive with the shoulders and the knees and the belt and the sword. And my young students with their sharp eyes can convince themselves, even with their naked eye, that it's not quite a point. It's actually a little bit fuzzy. It's one of those things that looks great even through binoculars. And I don't have to tell you folks this. People think you need like enormous telescopes to see amazing things, and that's not true. Even binoculars, Orion starts to look pretty cool. Of course, you really want to see the Hubble view. I know you do, so we'll just get onto it without any further delay. The Orion Nebula is also forming stars. In fact, their little trapezium there in the middle are brand newborn stars, and that's all the energy that's pumping out into the nebula, although you can still see lots of that dark part. It's relatively nearby. It's only 1,500 light years away, so it's pretty big across, actually. It's like half a degree, which is pretty big. So Hubble was not designed to take huge, broad pictures of the sky. That's actually best done from here on terra firma. But this is from, it's interesting, I wanted to point this out, this is the Hubble Space Telescope Orion Treasury Project team, and that's because they actually had to mosaic a whole bunch of different pictures together, and it took over 100 orbits of the Hubble Space Telescope to put this picture together. So as beautiful as this is, I think the even more beautiful picture has the infrared from Spitzer overlaid, and this may be one of the most beautiful pictures that NASA has come up with orbiting telescopes. This is the heart of the Orion Nebula in optical and all those little point sources in the infrared. And if you zoom in, this is what you begin to see. All over through the Orion Nebula are these little globules, these little brand newborn stars. And you also see remnants of the interstellar medium from which they formed. And as you look around, you see this little sideways thing, and this little sideways thing, and then this little sideways thing. And you start to realize that what you're looking at are these little disks. The stars are spinning, and what's left over forms a disk of leftover gas and dust. What happens to that leftover stuff? well, becomes planets, and it becomes college professors.
So did you say like a Bok globule is like an area where there's a star forming?
So the globules are actually very big. These little guys are very, 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 very small. These become now sizes of solar systems, not light years, but light days. Or, so we're 8 light minutes from the sun. So this, if you looked inside of a Bok globule, you might see this happening on the very teeniest scale. So in the beginning, infrared astronomy was not high resolution, and that's where a lot of the progress has come. It's very hard to do infrared astronomy from the ground because the sky blocks out most of the infrared light, and so taking these things up into space and being able to do them in space really helped the resolution. So these are very, very small. I think another, interesting piece over my career as I go to astronomy research meetings, it's been interesting to see how things evolve. And right now, the big topic is planets. And when I first started teaching, there were no planets. There were 9, and now there's 8, but that's another story. Okay, so, but now, and then I remember when it cracked 100. And now I don't even tell students anymore how many planets there are, because unless I just checked it, I'm going to be wrong, because we're finding more and more ones every single week. So we actually realize now that planets forming out of these disks is not just like a once in a while kind of deal, but it actually happens all the time. And these are called exoplanets or extrasolar planets, or as I like to call them, former dust. Okay. So let me tell you a little bit more, though, since the subtitle of this talk was The Life Cycle of Stars. Let me tell you a little bit more about that. So where does dust come from? It actually forms in the death of stars. This is a picture. See, there's no caption. Oh, right, I took this picture. Okay, I'm a better teacher than astrophotographer, I promise you. If there are any taxpayers of the state of Washington here. I'm an excellent teacher, but I'm learning astrophotography, so I was pretty proud of this because this is my first one. But if there's a ring there, and the little dot in the middle is called a white dwarf. And it's a dying star that has run out of fuel in its core, and it is shedding its outer layers. And it's in those outer layers, here's a slightly more famous picture of it. It's in those outer layers that dust grains form. And they're forming from the material that the star has been making over the star's life. What stars do is they take lightweight elements and stick them together to make heavier elements. And those heavier elements, like soot, the carbon in soot, and the sand, the silicates in the sand, the things that make up, terrestrial planets, and you and me, that stuff is being generated in these stars, and when they die, they spew that extra material back out into the interstellar medium. And sometimes it's not even really that polite how it does that. So here's the Orion Nebula again, and I'm showing this movie partly because I want to advertise this. He's a Seattleite. His name is Nick Reisinger, and he's done another AllSky Survey, but he's made it. If you just Google Sky Survey or go to skysurvey.org, but you can actually drive around. So let's see if this works. You can actually drive around in the survey. You can actually zoom out, which is what I do here, and you can see that our Orion Nebula is in this big ring. See that red ring? That ring is called Barnard's Loop, and it's the remnants of a star that didn't just, politely shed its outer layers, but actually imploded into a supernova. And it's in those types of dying stars where we get the really heavy stuff, where we get things like iron and heavier than iron. And those are really big. Those are really big. So here's yet another composite of Spitzer and Hubble, and this one's the Chandra X-ray. Is sort of they're the three amigos there for looking at these objects. And X-rays because this was a very violent explosion, and there's quite a bit of energy left over. So to summarize, right, the interstellar medium comes from the death of stars, but it's from these clumps of the interstellar medium that collapse down due to gravity, and they're cold, and they're dense, and they get even colder and denser and denser and denser and denser, and gravity wins and then makes new stars. And then they do that, if in the case of our sun, for 10 billion years, and then that star dies. And so what's happening is that the interstellar medium we see today is getting richer and richer and richer with these heavy elements from the death of these stars. So when I first started teaching, and we were talking about today at dinner that Hubble launched my freshman year in college. So when I first started teaching, I heard it said that every astronomer has their favorite Hubble picture. And I thought, well, it's silly. Until I found mine. And this is mine. The title of this picture is actually where I stole the title of this talk. Astronomers saw this picture. They were trying to study something very specific here, but when somebody looked at this picture, said, you know what this is? This is the life cycle of stars. Because what's happening here is that you see like these dark blobs down here, these little globules, right? These are the things that may be collapsing deep down within them to form new stars. The cluster of stars that you see here are hot stars formed from an earlier generation of the interstellar medium. And the hottest, most massive star in the set is already dying. And you can tell because it's letting these little wisps go. And those little wisps that it's letting out are going to become the next generation of dust and gas to make the next generation of stars. So Joni Mitchell was right. We are stardust. I promised that I would tell you a little bit about what's new in dust. So here are a few things. A few things that are new in dust. People who study all different kinds of things in the distant universe have to look through our own Milky Way to see them. And our Milky Way is really dense as a flat round thing, but see all these little wispy parts? That's also dust and gas. This is a picture of the reddening due to dust. So let's say you were going to look at quasars or galaxy clusters, and you want to measure their color. You need to know how much they have been made more red by that nearby neighborhood Milky Way dust. And these maps are really hard to make because that dense dark blobs, those are easy to find. The ones that make stars, instead of looking yellow, look slightly orangish, that stuff's harder to find. And so one of the things that my collaborators and people who don't even know me all over the world are working on is to try and make these maps better. One of the things that people are doing is doing these AllSky surveys, not just in photometry, but spectroscopy. And they're measuring hundreds of millions of stars, and they take plates, metal plates, at the focal plane of their telescope, drill little holes, and put in fiber optic cables so they can measure the spectra. And what they can do then is measure the types and locations of all of these different stars, maybe because you want to understand stars, maybe because you want to understand the history of the Milky Way, or in my case, maybe you want to know where this dust is. So one of the other projects that's doing the same thing is taking 800 million stars to map dust in 3 dimensions. This is the Panstars project on Haleakala in Hawaii. And here are some very early results. Now these results are, what I'm showing you here is that same map of the Milky Way. It's not the whole Milky Way, but it's a big chunk of it. And each of these little blips here shows you where there is some dust and gas. Now, it might look to you a lot like that other map. That was just, like a map, right? But here's what these folks have done. They've made 3-dimensional movies. So now we can start to see, where is this dust? Some of it's quite nearby, actually. That was a tilt movie. Here's this one. Now you'll notice that you see these long bars here, and that's because We see a great detail on the angle of the sky. You can tell little differences apart on the sky, for those of you who were taking that class earlier. The distance is really hard to measure. So it has a fundamental lack of precision in the distance axis, but a lot of precision in the angular axis. Keeps repeating on me. This will be the last one that I show today. So Sol is where we are, and you may recognize some of these clouds, the ones in Taurus, the ones in Perseus, the ones in Orion. So this is starting to show us where we are in the universe. So I think that this is as close as we're going to get for a while to interstellar exploration. But what we can do with these large data sets is an important piece of that. It's not as interesting maybe as hopping in a spaceship and zooming off to Alpha Centauri, but we can start to understand a lot about what the universe looks like, where these things are, you know, how the universe and our galaxy came to be the way that it is. Okay, and I cannot resist showing at least one example from one of my students. This is Holly Christensen. So for those of you who are faculty in astronomy programs that have a graduate component, Holly Christensen. She's awesome. She's an undergraduate. She presented this work at the American Astronomical Society meeting. And what she's showing here, what she's showing here is how certain you are about the type of background star is going to determine how well you know the dimming of that star. And so she made a set of models with background stars and said, what if you're not exactly certain what the background star is like? How well do you know the dimming of that star? And so she's doing computational models here, but she can help us understand a lot about the effect that dust has on our observations, not just of stars, but of the distant universe. And finally, just in case you think that nobody's studying dust anymore, it's old news. Anybody hear about this? This came out just last week, just January 30th. And about a year ago, there was a huge announcement. The BICEP 2 experiment from Antarctica said they had found the signal from the early universe, the inflationary expansion era of the early universe, and last week they had to recant. Why? They forgot to take into account the dust. Hence the title, Evidence for Cosmic Inflation Theory Bites the Space Dust. It turns out that they were looking at evidence from the early universe that looks a lot like warm dust. This is the far infrared emission from warm dust. And you can see it's all over the sky, and they hadn't fully taken it into account when they looked at the polarization signal. So there's a line I really like in here, and it says that the expansion after the birth of the universe was actually caused by something much more mundane, interstellar dust. So I hope that I've convinced you that maybe mundane is overstating a little bit, but that it's actually very interesting in its own right. And though it's quite a nuisance to astronomers, it's a great opportunity to learn more about the universe in which we live. So I really want to thank you for inviting me here today, and I'm happy to take any questions.